Here's the way that Newton first figured out that the same force that causes an apple to fall from a tree onto his head is what keeps the moon circling up in the sky. Imagine you have a cannon, and it's sitting right on top of the Earth. It's a huge cannon, just right smack dab on the North Pole. And you fire the cannon at not too big of a velocity, and you see it kind of, the cannon's firing horizontally, and you see it kind of arc and then fall to the ground, like you're used to. With the only force after it leaves the cannon acting on it is gravity, so it only acts in the downward y direction. The x velocity is undisturbed, and you end up just seeing a parabolic arc as it falls and hits the ground. So you think, well, that was pretty neat. I'm going to try to launch a cannon even farther. So you fire with greater speed, and it arcs back to Earth at a greater distance. And in fact, the faster and faster you fire it, the farther and farther it travels. Eventually, you'll be able to fire it so far, it begins to curve around the side of the Earth before hitting. And eventually, beyond that, you'll fire it so fast that it travels and curves and arcs toward the ground, but doesn't actually get any closer, and then ends up hitting the back of the cannon. It traveled all the way around the world and didn't land because it had just that much horizontal velocity to keep it up. That's all that orbit is. It's something falling toward Earth and missing. And Isaac Newton, way back in the day, came up with this idea, which is just incredible to me. I would not have thought, as I watched the moon up in the sky, that it's the same force that brings an apple down. Now, I mentioned from Newton's cannon that you need a certain velocity. Anything lower than that, you'll start to spiral in and hit the Earth. Anything more than that, and it'll eventually just come out of the cannon, kind of slingshot around the Earth, and make its way away. That's not exactly true. There is a range of velocities at which you would get some sort of elliptical orbit. But if you wanted a perfect circular orbit at a certain distance, here's how you'd find that out. In that case, the force of gravity between Earth and the object that you care about would be a centripetal force. And anytime something is designated as a centripetal force, anytime a force causes something else to move in a circle, it gets to wear a little badge that says equals mv squared over r, where m is the mass of the object moving in a circle. So it turns out it doesn't matter what the mass of your orbiting object is. If you know how far away it is from the center of Earth, and you know Earth's mass, and you know the value of g, you can solve for the velocity that is required to keep it going in a perfect circle.